would like to invite Mr. Tanmay for the presentation of paper ID 431 titled Cognitive AI Driven Intrusion Detection System with Real-Time Adaptive Response and Explainable Threat Intelligence. Please give a warm welcome to Mr. Tanmay.
Good afternoon, everyone. My name is Tanmay, and I am presenting alongside my co-researchers Angel and Krishna Pandey under the mentorship of Mr. Karamdev from the Department of Artificial Intelligence and Machine Learning. So today we are presenting a research titled Cognitive AI-Driven Intelligent Intrusion Detection System, a network-based real-time threat detection framework that combines ensemble machine learning with reinforcement learning-based adaptive fusion and explainable AI. So the cybersecurity threat in landscape is evolving faster than our defenses. In 2024 alone, the global cost of cybercrime has surpassed 9.5 trillion US dollars, and this figure is projected to cross 10.5 trillion by 2025, and the record of 2026 is still not. At the heart of this problem lies a fundamental flaw in how we detect intrusions. Traditional signature-based tools like SNOT rely on pre-catalog attack problems. They work well against known threats, but they miss approximately 30% of zero-day attacks because by definition, a zero-day has no existing signature to match it. Existing machine learning-based approaches improve on this, but they suffer from these critical shortcomings. First, single classifiers generalize poorly across diverse attack types. A random forest tuned for DDoS misses slow rate infiltration attacks. Second, fixed ensemble weights cannot adapt. When network traffic patterns drift over what worked last month may fail today. The third one is black box alert creates no analyst trust. When an idea simply says this is malicious without explaining why, security analysis override or ignore up to 40% of others. Our objective was therefore to build a system that addresses all four of these gaps simultaneously, combining ensemble for higher accuracy, using reinforcement learning to adapt fusion weights on the fly, provide sharp explanations per alert, and do all of this in real time at enterprise scale throughput. Greater than 10 gigabits per, 10 gigabits per second with under 15 milliseconds of latency. Prior research has progressed through these three clear generations. Earlier work, then in 1987, Royce Smart in 1999, established the signature-based foundation. A second wave in the 2000s applied traditional machine learning, decision trees, SVMs, Knight Weiss, who at 2008 showed error boost significantly improved detection rates on KDT datasets. The third generation, from 2017 onward, brought deep learning, CNNs for traffic image classification as demonstrated by Kim et al. 2020, and LSTMs for sequential flow modeling by Yim et al. 2017. These improved accuracy but introduced significant interface latency unsuitable for real-time deployment. The critical gap we identified is this: no prior system combines adaptive reinforcement learning-based fusion with per-alert sharp explanations in our real-time network ideas. That gap is precisely what our work addresses. Proposed architecture. Our architecture is a five-stage pipeline. Let me walk through these stages. Stage one is traffic capture and pre-processing. Live network traffic is ingested via mirror code or a PCAP file using lit PCAP. Flows are reconstructed from raw packets and Z-score normalized as rolling 60-second window to handle traffic shift. Stage 2, hybrid feature extraction. We extract 78 flow level features, inter-arrival times, byte counts, flag distributions, and augment them with deep packet inspection, payload histograms, giving us a 334 dimensional feature vector per flow. Stage 3, ensemble classification code. Three base learners operating up in parallel: a random forest, an XGBoost, and XGBoost classifier, and an LSTM network. Each produces an independent probability score for every flow. Stage 4, reinforcement learning arbitrator. Rather than averaging the three scores with fixed weights, our RF arbitrator dynamically learns the optimal weight for each base learner depending on the current traffic. Stage 5 is explainable alert and response. When a threat is detected, the system generates a structured sharp annotated alert, injects an ACL block or a net CNF and forwards the alert in CEF format to a SIEM, all within 15 milliseconds of the flow being captured. The next slide explains the methodology. RL arbitrator. The RL arbitrator is the core innovation of our system. Let me explain it using the Markov decision process formulation. So, according to this, we model the weight selection problem as sequential decision-making task. At each time step, the state is the contaminated prediction errors of our three base learners: random forest, XGBoost classifier, and LST, computed over the last 100 flows. The action is a weight vector produced through a softmax output, so the weights always sum to 1. The reward signal is the F1 macro gain over a sliding window. If the weighted fusion improves classification quality compared to the previous window, the arbitrator gives a positive reward. What does this look like in practice? During a DDoS attack, the arbitrator shift towards heavily towards random forest XGBoost, approximately around 0.45 and 0.38, because volumetric attacks are captured whereby tree-based feature importance. During a slow stack or botnet, the LSTM receives the highest weight at 0.51. This adaptive behavior is what gave us 4.5% of F1 improvement during concept drift phases compared to a fixed weight in 7. These are the implementation details. So, what we used throughout the process is Python 3.1, 0.1, scikit-learn, XGBoost, and all these for feature extraction, we use litpcap for live capture, CI/CD 2017 and 2018 datasets, and in several models, random forest, XGBoost, and LSTM, as I mentioned earlier. RL training, policy gradient, two-layer MLP, a sliding window, check explainability, free explainer for RF and NGB, a deep explainer for LSTM. Deployment, Ubuntu 22 server, libpcap mirrored port, and throughput greater than 10.4 Gbps measured on a 10 GB test bed, lesser than 15 milliseconds end-to-end SIM latency. Now comes the step is, now the next slide says data sets and evaluation set. We validated our system on three widely accepted benchmark datasets to ensure our results are reproducible and comparable to prior. CIC IDS 2017, CIC IDS 2018, and UNSW NB50. Our pre-processing pipeline applied SMOTE oversampling for minority attack classes, random undersampling to achieve a 70-30 gain to attack ratio. Our baselines were not 3.0 with the emerging threats rule set, representing the production standard and standalone random forest and LSTM models, representing single classifier baselines. Results and performance. Our results speak clearly. On CIC IDS 2017, AIDS achieved 98.9% accuracy, and on 2018 one, it was 98.7% accuracy, and on UNSW NP50, 97.4% accuracy. Across all the datasets, our false positive rates remained below 0.9%. Critically important because false positives are what cause alert fatigue and analyst burnout. Our system also demonstrated throughput exceeding 10.4 gigabits per second, making it suitable for enterprise deployment without dedicated hardware explanation. The explainability. This slide shows a real structured alert generated by a system for an SSH brute force attack. Let me walk you through. The alert correctly identifies the threat as brute force over SSH with 97.3% confidence. The source IP is 203.0.113.47. Was attempting to authenticate against our target at 10.0.1.15 on port 22. Below the classification, you can see the individual base level scores. Random forest scored 0.981, XG boost 0.968, and LSTM 0.971. All three models agree strong. The RL arbitrator assigned weights of 0.41 to random forest, 0.32 to execution, and 0.27 to LST, reflecting that this is a connection pattern attack where three models have an advantage. This matters for three reasons. First, analyst trust. 94.2% of our analyst evaluators confirm these top five features match their domain knowledge. Second, auto response. The ACL block was injected in under 10 seconds via net CONF, no human brain required. Third, SEM integration. The alert was forwarded in CE format compatible with both Splunk and IBM URL. Now the conclusion. Conclude your presentation. So to summarize, we presented AI IDS, AI-powered intelligent intrusion detection system, a network-based real-time intrusion detection system, जो कि हमारे इसमें हमारे तीन बेस लर्नर्स थे, रैंडम फॉरेस्ट, एक्सक्यूज क्लासिफायर, एलएसटी। हमने तीनों बेस मॉडल्स पे ट्रेन किया और उनकी एक्यूरेसी 97.9, 97.7 and 97.4 पे थी। Can you go back to the graph? I cannot see attributes here. So we use data sets, three different benchmark data sets. So can you tell the limitation of IDS? Limitations.
We appreciate the presenter for sharing such valuable research paper. Now I would like to call upon Ms. Ananya for the presentation of paper ID 515 titled Automated Road Condition Assessment in Mountainous Regions Using UAV-based imaging and machine learning. Please encourage Ms. Ananya with your applause. A very good afternoon to everyone. I am Anya along with other contributors, Ms. Shakha, Mr. Sharma, under the guidance of Ms. Gurpreet Kaur and Ms. Savita ma'am, are presenting the research on the topic automated road assessment in mountainous regions with deep learning techniques. Imagine if you are traveling through snowy mountains with no idea of weather and landslides ahead. This is where the current system lacks. So, our research focuses on deep learning to detect road conditions in mountainous areas, improves accuracy in bad weather conditions like fog, rain, or snow. Apparently, everything was based on my manual inspection or only urban-focused AI models, not suited to mountain terrain. Here, we are using camera satellites and images to detect potholes, crack slides, and damaged road automatically. That research is excellent, especially to the tourists. This research benefits us by doing faster road inspection, reducing manual efforts, improving road safety, and support for timely maintenance. The dataset for the research has been collected from ISRO scheduled datasets and government historical data. The architecture collection includes data collection, pre-processing, feature extraction, segmentation, classification, GI visualization, mobile web interface. Deep learning architecture includes CNN, that is computational neural networks, YOLO, ResNet 50. We are using CNN with transfer learning because it performs very well in image classification by reducing training time. The challenges faced in this project includes model generalization, bad weather conditions, lighting variations, sharp turns, and many more. Internet and connectivity problems, high training time. The future scope of the project focuses on drone integration, real-time monitoring, IoT sensors, GIS integration. And
What about your data science?
sorry,
Data science.
the leadership side is around the on trackers 5,000 data
How
available.
many images you process?
It's around 10 to 15 images. We
10
are
to 15 images.
we are
How
focusing
much
on
after data augmentation? How much after data augmentation? And data testing? How much will increase?
next round 3 years after in this 1 year, so 4 to 5 months. 4 to 5 months. Thank you for a wonderful presentation. Now I would like to call upon Harshita for paper ID 478 titled Cryptocurrency Portfolio Tracker. A huge round of applause for Harshita. Good afternoon everyone. I am Harshita presenting a research paper on secure cryptocurrency portfolio tracker with our guide between ma'am and my two fellow members, Mathematics and Rajishma. So, after investing in cryptocurrency, the tracking and management becomes very difficult for us because we have different coins in different platforms which have different brokerages and they are not even beginner friendly. So, so here we are introducing our project Secure Cryptocurrency Portfolio Tracker. While researching, we get to know that most systems lack real-time synchronization, have poor analytics, they are not even user-friendly and they are very complex. Our objective is to build a centralized and user-friendly portfolio tracking system which integrates real-time data and automate financial calculations. Our system follows a structured workflow. Step 1. User enters cryptocurrency details such as coin name, prices. Secondly, the system integrates APIs such as Binance. Thirdly, the system processes the data and automatically calculates current assets, portfolio value. Moreover, the portfolio information is stored using databases such as MongoDB. Then visualization tools like pie chart and graphs are introduced. Finally, final steps, the user receives a real-time dashboard with complete insights. The previous apps like Coin Market and Delta provide a basic tracking functionality. There is no decision making and neither they provide information of all ones. They rely on manual data. So our project try to overcome all these problems by reducing manual effort and human error, improving decision making so that our portfolio tracker provides an efficient and centralized solution for managing digital asset investments. To conclude, the proposed cryptocurrency portfolio tracker provides a centralized and efficient solution for digital assets management. The key achievement of this work is the development of a simple, user-friendly, and real-time tracking system that assists investors in making better financial decisions. Thank you.
What is the difference between Bitcoin and Ethereum?
So Bitcoin is basically a cryptocurrency and Ethereum is both are same, but actually Bitcoin is Our more independent freedoms are developing. Thank you for the wonderful presentation. Now I invite Mr. Sri Bhagwan for the presentation of paper ID 415 titled A Comprehensive Study on Machine Learning Driven Smart Water Conservation and Management Device. Please welcome Mr. Sri Bhagwan.
Good afternoon, everyone. My name is Shiruman, and today I will be presenting a review paper titled A Comprehensive Study on Machine Learning Driven Smart Water Conservation and Management Devices. This paper studies how AI, IoT, and machine learning can help in smart water conservation and management. Water scarcity is one of the major problems across the world. The main reasons are rapid urbanization and population growth and climate change. Because of these challenges, traditional water systems fail to provide real-time monitoring, leak detection, and automated control. To solve this problem, researchers across the world have started using IoT sensors, machine learning, and artificial intelligence to build smarter and more efficient water management systems. However, after studying the existing work, we found one major gap. Most systems only monitor or predict. Most systems, very few systems combine monitoring, prediction, and next like leak detection. For this paper, we have reviewed multiple research papers published between 2021 and 25. Let me highlight a few of them. Mammoth et al. Developed an IoT framework for real-time monitoring and automatic pump control. Mochit et al. Created a smart irrigation system using soil moisture and weather data. Snelly et al. Designed a wireless IoT sensor network for monitoring water quality and pressure. Joseph et al. Applied machine learning for early leak detection in water pipelines. Overall, these systems improved efficiency, but most of them worked separately and did not combine monitoring, prediction, and automated control together. Over the years, smart water management system has progressed in these major areas. IoT sensors are now provide real-time data on flow, pressure, and water quality. Machine learning models analyze this data to predict consumption patterns and detect anomalies. Smart water irrigation systems use soil and weather inputs to water the crops only when actually needed. Automated valve and pump control removes the dependency on human operators. Cloud computing allows all this data to be stored and analyzed centrally. And finally, integrating AI IoT platforms are now combining all these capabilities together. So fully autonomous systems are still being developed and improved. Despite all the advancements, there are some serious challenges that are preventing widespread adoption of this technology. The challenges include high installation costs and maintenance costs, cybersecurity risk in IoT connected systems, poor sensor data quality affect ML accuracy, connectivity and infrastructure gap, lack of scalable and interoperable platforms, and connectivity issues. And the most
Can you
important
tell me the sensors that can measure soil moisture?
Sir, I don't remember the exact.
Thank you. Thank you for the wonderful presentation. Next, I would like to call upon Mr. Yogendra for the presentation of paper ID 462 titled Image Classification for Early Respiratory Disease Prediction. Please welcome Mr. Yogendra with applause.
Paper ID क्या है आपके? 460. Good afternoon, respected judges and all the participants here. I am Yogendra Katwal, CSC Department of SMR Institute of Technology and Medicine. Today I am here on the stage to present our research that is based on image classifications for early respiratory disease prediction. So I will begin with introduction, then followed by literature survey, then methodology, then we will discuss the result and discussion, and I will conclude the presentation with conclusion. So basically, respiratory diseases are such as like tuberculosis, and pneumonia, and COPD and lung cancers are still the major health burden in across the globe. So annually, around millions of deaths are happen. So this is the the big problem, and one another big problem is that we find in our research is chronic diseases is the long term and they are silently progress inside the human body that are when they are showing their symptoms they are in a critical situation, so it is late for the diagnosis and it is burden the some healthcare expertise such as radiologists. And so AI based and deep learning techniques is it was fast and accurate so that to predict into the early stage and they increase the survival rate of the disease. And the research gap is also we will see that during the research that is traditional machine learning have the manual feature extraction, which is it has no automatic and deep learning has the automatic feature extraction, but the traditional method has time consuming and it is not giving the better accuracy to predict the in the early stage of respiratory. And our main objective is to achieve early and accurate detections of respiratory disease in the early stage using the deep learning and feature extraction from medical images. These are the some literature reviews that we see. And this is the pipeline of our proposed methodology. First of all, we collect the data from CAGR that consists 3,475 images of CT scan and chest X-ray. The data set name is long X-ray, and it has label data because it classified into three sections.
I have two questions to ask you. What is the difference between X-ray images and CT scan images?
CT scan has a high resolution 3D images, and just X-ray is they are even available in the and it is more cheaper than CT scans.
I'm talking in terms of image.
In terms of image, CT scans like जो कि ज़्यादा like जो इसके symptoms होते हैं उसको ज़्यादा डिटेलिंग और 3D मॉडल्स में दिखा देता है, but just X-ray is 2D images उसे like एक आउट लेयर ही दिखा देता है.
And what is this 169 with density?
Yes sir.
169 is covered?
Sir, density 169 is the deep learning model.
That's okay. What does 169 represent?
So basically, after the while we see into the result sections, there we apply the density 169 model to compare and to achieve the higher accuracy.
Sir, I agree to this point. What does this term 169 with density represent?
The density conditioner is an advanced model of density system, and it is the direct connection between the layers. And this is the methodology architecture of our model. Next one. Thank you.
Thank you for the wonderful presentation. Next, I would like to call Mr. Prithvi for the presentation of paper ID 476 titled Smart Waste Segregation Monitoring System for Urban Local Bodies. A huge round of applause for Mr. Prithvi.
Good afternoon, everyone. I am Suji Pisa, presenting my topic on smart waste segregation and monitoring system for urban local bodies. In today's world, one of the biggest problems we face is waste management. With increasing population and urbanization, cities are generating a huge amount of waste every day. If we look around in our daily life, we see overflowing dustbins, bad smell, and unhygienic conditions. This will not only affect cleanliness but also leads to serious health and environmental issues. One of the main problems with the current system is that waste is collected at fixed schedule, not based on actual need. Sometimes people are already full and still wait for collection. And sometimes trucks even come when the bin is empty. Can you talk about that? So इसमें क्या है कि हम presentation study कर रहे हैं। ये मॉडल है ये ये तरह का नहीं सर ये एक शो के लिए डेमो का नेक्स्ट सर इसमें हमने IoT बेस पे करना है इसको लाइव डेटाबेस से कनेक्ट करना है वेबसाइट से तो हमने सेंसर्स के थ्रू सिस्टम बनाया है जो कि वेस्ट को डिटेक्ट करता है और उसको सेग्रीगेट करता है ड्राई और वेट में और इसका लाइव डेटा जो है वो वेबसाइट पे शो होता है यूजर को और जो भी ये पहुंच जाता है तो इसकी लाइव लोकेशन ट्रक ड्राइवर से आती है जो कि शॉर्टेस्ट पाथ से उसको वेस्ट को कलेक्ट करता है ये तो इसके वही है जो डिसीजन की अभी जितने भी रिसर्च हुई है उसके पार्ट में डिवाइड किया कितने पार्ट में सेग्रीगेट करेंगे तो इसको हां ड्राइवर फिलहाल ड्राइवर में कुछ अपने मैटर और उसके ऑर्डर प्रोसेसिंग के नेक्स्ट कौन है
Thank you for the wonderful presentation. Next, I invite Mr. Akshat Pandey for the presentation of paper ID 684 titled DL Thermal Imaging for Top Drought Classification. Please welcome Mr. Akshat Pandey.
Good afternoon, one and all present here. I am Akshat today, going to present my topic on drought stress detection in crop using thermal imaging and deep learning. This work focuses on an important agriculture problem, detecting drought stress by early so that the farmer can take timely action and prevent crop loss. Drought stress is a major factor affecting the global productivity. Traditionally, drought is detected using methods such as soil moisture and manual field inspection. These methods are useful, but they are time consuming and labor intensive and difficult to apply on large agricultural fields. This is where thermal imaging becomes useful. When a plant experiences drought stress, its temperature pattern changes because of the reduced transpiration. These cameras can capture the temperature variations and deep learning models can learn the pattern from those images. In our studies, we identified some key research gaps. Many, many previous works are limited data sets, focused only on a single crop, or have proper comparison with the models and were not designed for real-time deployment. So our objective is to develop a scalable deep learning framework for broad detection using large multi-crop thermal imaging datasets and to make it suitable for real-time based deployment. This, this slide summarizes the existing approaches for drawing stress mission. A strategy includes our methodology has four main steps. First, we use a large dataset of more than 50,000 thermal images collected from crops like maize, wheat, and soybean under real field conditions. Second, the crop water index, stress index, was used for labeling the images into different drought stress levels. Third, we propose a hybrid CNN telephone to control our proposed framework, improve the draw, stress detecting using thermal imaging and deep learning. The hybrid CNN plus transformer model captures the both local thermal features and global image context, which improves the classification accuracy. Finally, the system is suitable for real-time based deployment and making it useful for practical precision agriculture. Thank you so much.
With this, we came to the end of the session one of the paper presentation. I sincerely thank all the presenters for sharing their innovative research and valuable insights. I would also like to thank our respected judges, faculty members, and audience for their presence and support. Thank you for everything. Now I would like to request Dr. Naveen Sharma sir, Professor of CSC Department, HMIITM, and respected session chair Dr. Ashish Sharma sir to come and present the momentum and certificate to best paper, and he is Arpit Dwivedi. With this, we came to the end of the session one of the paper presentation. I sincerely thank all the presenters for sharing their innovative research and valuable insights. I would also like to thank the respected judges, faculty members, and audience for their presence and support. Thank you for everyone. Have a wonderful day ahead. All the participants are requested to collect their certificates from this site as soon as possible. Thank you.